have the 75 pages of the report. I can't cover everything in 1 hour. I can talk about it for hours. So I'll just cover what I focus on as a data scaling and model scaling. First, I'll do an introduction of Cosmos for people who are not familiar with. I guess the introduction is best through Jensen himself.
Physical AI. It includes auto-regressive world foundation models, diffusion-based world foundation models, advanced tokenizers, and an Nvidia CUDA, an AI-accelerated data pipeline. Cosmos models ingest text, image, or video prompts and generate virtual world states as videos. Cosmos generations prioritize the unique requirements of AV and robotics use cases, like real-world environments, lighting, and object permanence. Developers use NVIDIA Omniverse to build physics-based, geospatially accurate scenarios, then output Omniverse renders into Cosmos, which generates photoreal, physically based synthetic data. Whether diverse objects or environments, conditions like weather or time of day, or edge case scenarios. Developers use Cosmos to generate worlds for reinforcement learning AI feedback to improve policy models, or to test and validate model performance. Even across multi-sensor views, Cosmos can generate tokens in real time, bringing the power of foresight and multiverse simulation to AI models, generating every possible future to help the model select the right path. Working with the world's developer ecosystem, NVIDIA is helping advance the next wave of physical AI.
Okay, so what's a word model? A word model, it takes the past observations X and also perturbations C. It can predict the future predictions. The perturbation can take any forms, like it can be actions from the physical AI, or it just can be some random perturbation, or a text description of the perturbation. So in the Cosmos 1.0, we open source a family of models. We have two sets of word foundation models. One is based on diffusion, while the other is based on autoregressive models. For each family, we also build two base models and two derivatives. To achieve the best generation quality, we also build prompt upsampler for the diffusion model and also diffusion decoder to improve the video generated from the autoregressive model. So these are already open source on GitHub. You can feel free to try. So for the diffusion word model, this is the architecture overview of it. So the input video goes through a video tokenizer. So now here is called the CV 8x8x8. Basically, the time spatial are both compressed by 8. If you have like 8 frames, it's going to go into 1 frame, and I assume everyone know diffusion. The tokens are corrupted, then go through a diffusion transformer. The model then generate the reconstructed video and during training. This is an example video generated from the diffusion word model. And for the autoregressive word model, it goes through a similar process. As a tokenizer, instead, it's discrete instead of continuous. Discrete tokenizer is very similar to LLMs. So this discrete tokenizer here, it converts video patches into one of the one of the in the vocabulary, there's a 64K vocabulary, and these discrete tokens are fed into a transformer similar architecture as LLMs, and then the discrete tokens are generated. Then there's a decoder, which is also a discrete decoder that decode these tokens into videos. There have been debate on whether like diffusion or autoregressive models are better. Since we don't know, so we build both of them. For example, here, this is a input image for the diffusion for the autoregressive model. You can use this as a pre-filling words for the transformer. Then in the decoding process, it can decode into videos. Autoaggressive, if you want better quality of the generative result, you can go with the diffusion model. If you want the model to be faster, you can try the autoaggressive model. And autoaggressive also play very well into like other modality. You can either easily combine other tokens like text tokens or action tokens. But here, our autoregression model is trained purely on videos. We also released post-training scripts for these models. Right now, we have in the Cosmos paper, we discussed several post-training examples of the Cosmos foundation models for different physical texts. So right now in the GitHub, we support general post-training. Basically fine-tune the word models on to generate a target distribution of the videos based on custom dataset. The target distribution could include a specific camera spec or a specific domain, such as factory. Um, Here is an example. So we took a few videos of a humanoid. Here it's an agility robot, agility humanoid, and just roughly like 5 videos of this humanoid. And the video is in simulation, but after fine-tuning the diffusion model, you can generate novel videos of this robot doing something else. The model is able to remember the characteristic of this robot, will generate novel tasks which are not possible in either simulation or in the real world through teleopt. And there are more post-training scripts that are coming soon. For example, instruction control, the post-train models for robotics manipulation to predict the video based on textual instruction. Like you can instruct the robots to perform some tasks like folding clothes or pick up objects. And also action control. The post-trained robots can like predict both the next video frame and the next action frame. And here the example shows the camera control. Adding the camera pose as condition, you can generate 3D consistent video simulation from single image or video. This can enable the joystick-like navigation in virtual environments. And you can also do multi-view generation for especially for autonomous driving. You can generate synchronized multi-view videos from text prompts, then simulate the driving scenarios with multiple cameras perspective. Next, I'll dive into technical details. First, I'll go over data scaling, then it's a model scaling. So we open source a training framework, and the NEMO, the data curation part, you can sign up for it. It's coming soon. Or the training framework are open sourced. For the When we curate the data for text, it's like you can just grab the text online, and the label is basically next token prediction, which is relatively straightforward and cheap to curate. However, for videos, for example, you have a video shot of someone playing basketball. You need to label a basketball player is dribbling the ball and shooting it into the hoop. Labeling video data requires good AI models for automatic captioning. We want to control the AI models to generate using text we specify. And also, another challenge is the video signals are less refined compared to text. Maybe out of like an hour of videos, there might only be a second of interesting stuff. This is very computationally challenging and very expensive. We use distributed computing to solve this problem. This is a life cycle of curation. So on top of DGX cloud platform, we use array data based on streaming pipeline running on thousands of GPUs. So the long video go into the pipeline, and the videos are splitted and then transcoded into shorter clips. Then different AI models are running on the shorter clips to detect high quality videos. And another NVIDIA VLM captioning model running using TensorRT LLM is used to caption the video. And finally, we get the training data set. Data curation for the video foundation models are very challenging. The scale of the video data are hundreds of petabytes, much bigger than the previous image models. Orchestration at scale, heterogeneous compute requirements of like tens of AI models running efficient together is also very challenging. Like you have the captioning model, you have models to detect the scene change, you have model to detect the video consistency, aesthetic, etc. Multiple concurrent streams of high throughput data exchange between AI models also impose bandwidth challenge to the cluster. Every single step of the uh, curation pipeline need to be GPU accelerated. And we also need to manage the resiliency of the GPU-based data pipeline at scale. So each inference model need to run at speed of light. We go from the baseline where the model is run on PyTorch to use TRT LLM to accelerate. And then we run it on larger batch to further accelerate it. And today we use FP8 quantization to further accelerate it to 7x compared to the baseline. The video understanding, so filtering the high quality clips and the auto labeling is not enough for building a video foundation model. We need to understand a lot more about the videos for like specific domains training. We remove the duplicated content and visual search understanding of the data. So these are the next life cycle of the video data curation. And after the captioning, we need to do clustering to group the data into different categories like sports, entertainment, robotics, etc. Then there is a semantic deduplication to remove the redundant data. Finally, video taxonomy to further help researchers to pick the data they want to train on. The takeaway for the video data curation is we built the video processing capabilities into NeMo Curator to enable the developers to curate high quality data and train highly accurate video foundation models. By leveraging end-to-end GPU acceleration and optimizing the data orchestration through the pipeline, NeMo Curator can scale to over 100 petabytes of data. Our optimization reduces the processing time and lowers the total cost of ownership. The models are optimized for high throughput and enhancing overall pipeline efficiency. Next, let's go over the model scaling. So using NeMo Video Foundation Model Training Framework, you can scale these video models up to 20 times larger than traditional frameworks. The framework is capable of training models like diffusion or autoregressive or foundation models up to 100 billion parameters. And the throughput is highly optimized. We achieve roughly 450 teraflops. That's about 50%, close to 50% MFU on the H100 chips. These are very close to the training efficiency of the LLM training. Okay, previously we talked about the scale of data curation. Like we have hundreds of petabytes of the data go into the curation pipeline. After curation, the data set we get are clips, video clips, short video clips, and images with the text embedding. So even though the scale of the data is much smaller, these are still considered relatively big if we want to train on the clusters today. For example, we have the images are on the 1 billion scales, and the videos are roughly 100 million video scales. In the paper, we use image and token and video tokenizer compression rate of roughly of 8 by 8 by 8. At this scale, the image are compressed to roughly 200 kilobytes, and for 1 billion images, it's roughly at the level of 100 terabytes. And for the videos, it's on petabyte level. Storing, so a solution can be storing this data on the cluster or storing them on like cloud storage like S3. Storing them on the cluster have some huge costs. Like most of the clusters, they don't have huge storage on the cluster themselves. So we provide both solution in the open source framework. We leverage Megatron Energon, which is another open source library from Nvidia to load data efficiently. So it allows you to load data from web source like AWS S3 very efficiently without the GPU idling during training. It allows you to deterministically save and restore the data loader, which is one of the biggest challenge in loading from the web dataset. In web dataset, usually the data is loaded sequentially. When your training is interrupted, uh, the traditional way of training, really you have to randomize loading. So you won't be able to load non-repetitive data without Megatron Energon. Another challenge in loading the data is variable input data shapes. We have the data type are different. You have image, video, and you also have like different durations of the videos. You have 1 second, 10 second, or even 50 seconds. And the resolutions are different, 360p, 720p, 1080p. There are also different aspect ratios, 16:9, 9:16. So when you're training on text, you don't have this kind of problem. But in video, this can cause a very big problem in efficiency. If we batch the data into traditional approach is batching the data. Like if we need to uh, so for each different shape of the input, for example, image, we batch the images uh, into a few samples of batch. And for the videos, for the very large videos, you can just take one video as input. For medium size, maybe you can batch 2 or 4 into one batch. The the pros is that this is commonly used for most of the models nowadays. For example, like in ImageNet training, traditionally people just resize all of the image into 512 by 512 to mitigate this problem. But the challenge here is um, if you want to train on different aspect ratios and different resolutions, you need a complicated data loading logic to ensure that during training, at each iteration, at least the data shape is the same. And the efficiency is not very high because not all of the data shapes can be efficiently utilized by GPU. And also constantly changing the shape of input data can cause challenge to the, the fuse kernels. It's on GPU, if all of your tensor operation shapes are the same for all the iterations, we can optimize for it and it runs more efficiently than dynamic shape. The data loading scheme we open source is called pack sequencing or sequence packing. So different from the traditional SBHD format, which this one allow you to use different image, video, multi-model, whatever, also different aspect ratios, duration, resolution. The key is to reshape all of the data into one-dimensional sequence and then pack them together into one batch. And when you pass this into transformer, outside of self-attention, there's no problem at all. Like the MLP operation of the transformer is just a per token operation. But for self-attention, we would need to create a block diagonal mask so that each of the sample in the sequence are computing self-attention on themselves. And this operation is automatically done on the fuse CUDA kernel. You only need to supply the sequence length in our training code. And that's all you need to enable pack sequence training. with this data loading scheme, the training efficiency is very high, and you can see in the end there is a padding. Um, if you have large enough max sequence, the padding is really very small, and the training efficiency is very close to when you have all of the samples with exact same shape. Next, I'm covering the parallelism. The training on videos is one of the biggest challenges the context lens. Traditionally, in pre-training LLMs, the context lens is really like 4K, nowadays 8K on Llama. But training on videos, the context lens is much larger. Say we have a 5 seconds of videos, um, encoding it with a 8 by 8 tokenizer, it goes into roughly 60K or 70K of tokens. This is 10 times larger than the sequence length of LLMs. Context parallelism or ring attention is one of the key technique we use to scale the diffusion transformer or the autoregressive word model to up to 1 million tokens. So using context parallel, you can split the activations of the entire transformer along the sequence dimension. This exploits the permutation invariance of attention to distribute the sequence in ring topology. And
Hey, quick question, Ethan. So
yeah,
I know for some LLM models, like even the Llama models that are trained up to 128K context, something that they do is they do the bulk of the training, like the majority of the 5 trillion tokens are done at a smaller context length. And then in that post-training, they continually train on longer context. Is that a thing in video gen? Like, can you train the majority of the model at a short, like clip length and then extend this and extrapolate it out?
yes, that's a good question. Um, I think the bottleneck here is we don't have a very efficient video compressor. So like even a 5 second video is like 60K tokens. And if we say we train on shorter videos like 1 second, that also works. But for majority of the training, um, the video foundation models, they are 10 times longer context compared to the LLMs. For post training, the video models are extended to even longer context, say like 1 million tokens, to be able to generate a video roughly like one minute.
Got it. Makes sense. So it's basically the same problem. It's just like 10x scale on both sides. So even the short context is still very big.
Yes.
Thank
Yeah.
you.
Yeah, I'd say if we have a very good tokenizer in the future that can efficiently reconstruct the videos, maybe the paradigm will change. Right now, the video tokenizer Cosmos release are 8 by 8 or 8 by 16 by 16. Um, so spatial wise, 16 by 16 is already near the limit. If you go beyond that, a lot of the reconstruction artifact will appear.
Makes sense. Thank you.
For for the video for video generation and inference, we also employ context parallel. In the open source repository, you can already use context parallel to accelerate the inference. For example, on 8 GPUs, using context parallel 8, you can generate a 5 second video under 30 seconds. And using more across different nodes, you can generate the video in a matter of seconds. Another challenge brought by diffusion transformer is pipeline challenges to pipeline parallelism. Traditionally, in LLMs, for different pipeline stages, you only need to pass the hidden states to the next pipeline stage. But diffusion transformers have a lot of conditioning and a lot like adaptive layer norm, and also conditioning on text, which create difficulty for the pipeline parallelism. So we provide a solution to generate the additional conditionings on each pipeline parallel ranks. This will use slightly more compute, but reduce the communication costs a lot, which leads to improved performance. Okay, I think that's all of my presentation. Thank you for listening. Any questions?
Hi, Ethan. Thanks a lot for the joining us again. This is RJ.
Thank
I
you.
asked a question. I asked a question at the beginning of the chat that I'm a little unclear about how the encoder gets like the encoder to the 8x8 latent space gets trained. Is that like just part of the diffusion training, or is there something like some sort of like a separate step that is used to train that encoder?
Yeah, that's a good question. So a separate step is used to train the encoder.
Okay.
Tokenizer is a fancy name of this, but this is vector quantized variational autoencoder, VQVE.
Okay. Yeah.
So yeah, you basically train it for the task of reconstructing the videos.
Okay. Right. So but how do you get it to create a 3D? What's it like the TLDR on how to get it to create a 3D latent space like that?
Yeah, so the model architecture itself is a causal convolutional neural network.
Okay.
It can reconstruct the encoder and decoder structure reconstructs the video. So the training
Yep.
objective is basically reconstructing the video. The
Mhm.
process is you need to collect some diverse set of different videos, ideally in your domain, and then train this causal CNN to reconstruct those videos. The code book here for continuous tokens are just those continuous tokens, but for discrete tokenizers, you would do vector quantization to quantize into 64K of code base.
Okay. Sorry, I didn't have time to pre-read the paper. Is this covered in the paper, or is there a separate paper for this?
Yeah, this is covered.
Okay, got it. Got it. Thank you. This is really super interesting, exciting work. Thank you very much for joining us.
So additionally, the tokenizer is freeze during the training of the transformer, because if you don't freeze the tokenizer, it can lead to catastrophe forgetting. Like you just generate if you just predict zero and the loss is zero.
Okay. Got it. Yep.
Sorry, I have also a question. I didn't find any reaction button that I can raise my hand. Can I ask the question right now?
Yeah.
Okay, perfect. So my question is about, the open source framework for pre-training that you mentioned. I think it was Nemo, right?
Yes.
Yes. So, do you think potentially, if I have a set of videos, but those videos originally they were not necessarily in the RGB space. Okay, so I don't know, for example, satellites or anything, spectral wavelengths or whatever. And, I just somehow map them to videos. Do you think, I can still customize your framework and just pre-train, my own tokenizer or basically whatever else, that exists in that framework?
Yeah, if your data domain is different from video, it's recommended to fine-tune the tokenizers.
So just fine-tuning, do you think you're gonna work?
So because if the tokenizer is not fine-tuned, it might produce some artifacts for your data if your data domain is different.
Mm-hmm.
And
And sorry, yeah, go ahead.
after fine-tuning the tokenizer, you might also want to fine-tune the diffusion transformer or autoregressive transformer. Yeah, both of these are supported in the framework.
Awesome. And I can also pre-train the tokenizer using the current framework or
Yeah,
fine-tune. Yeah,
yeah.
perfect. Awesome. Thank you.
Thanks for the presentation. I had a quick question related to some of who you mentioned was coming soon for multi-view generation and more camera control. So curious if you could speak any more towards how you're approaching multi-view or how to make sure that the camera intrinsics correlate between one another. If they're all video-based generation versus having a true like grounded scene understanding, how you guys are approaching that.
Yes, that's a good question. So these are coming soon, but the techniques are covered in the paper. For example, for multi-view generation, the different number of views are folded into one of the dimensions in the data. So the model input is still roughly the same. It seems to fact is falling into the time axis. And for the camera intrinsics, it's not used now because if you have a consistent intrinsics, you don't have this problem. But if your intrinsics is going to change across different training data, I guess it's helpful to include that in the conditioning information. At least in the example, we use consistent intrinsics.
Got it. So you're saying it has more to do with perhaps more the training data that you're using to post-train these models to have it be consistent and have similar intrinsics. Is that sort of what you're saying?
Yeah, yes.
Is that right? Okay.
I can answer questions in the chat. Yeah, I wasn't looking at it. Yeah, so what does a token represent in this case? 1 pixel of video. So the tokens are a patch of video. Say for image, 8 by 8 patch is 1 pixel. For video, 8 by 8 patch is 1 token. That means roughly for 1 second the video is if it's 30 frames, and in the time domain you have like four tokens, and spatially that depends on your resolution. Because the video doesn't have a depth map, but you can add it in the post-training process. What's the difference between post-training and fine-tuning? I'd say like post-training is a fancy word of fine-tuning, and now fine-tuning specifically reference to like without special techniques, like just continue pre-training. I'd say these two words are interchangeably. Oh, number of tokens for each of these foundation models trained. So for pre-training, it's a 100 million video clips level. And I have the equation in the, and according to, so each video clip is roughly 5 seconds, and using that information, you can calculate the number of tokens. I say it's roughly on the scale of like 10 trillion, at least 10 trillion tokens or more. You can calculate it yourself. Yeah, what type of hardware is adequate for post-training on our own data? So the post-training of the open source now need like eight H100 for diffusion and 2 H100 for the autoregressive model. But with some technique like activation offloading or LoRa, I believe lower end GPUs can also be used for post-training. So the word in our model name, we want to emphasize that the model has spatial consistency, and we're aiming to provide the best foundation model for robotics post-training. Okay, I think that's all the questions in the chat. Any more questions?
Hi, Ethan. Thanks for the talk. I had a question. So, for you said for identifying high quality videos, you high quality clips, you filter them out first, right? How do you do that? Do you use like some already available open models, or do you train your own models for that?
Yeah, that's a good question. So there are different metrics for filtering videos. There are both heuristic and some models. Heuristic, like if the video is static, it's basically image is not a good video, or you can also train a model to classify the quality of this video, like aesthetic score. So that might need some other training and labeling. And also motion scoring, like how much motion is in the video.
So, in your case, you guys trained a custom model for that based on these metrics, maybe motion or based on the aesthetics.
There are a lot of like available models open source already. You can check it out. Like there are aesthetic classifier, etc. Yeah.
Okay, thanks.
Another quick question is, as Cosmos develops or releases more iterations, how do you foresee approaches to adding more controllability within the scenario? So more refined control over what's happening in the scene and what variables you want to change versus not to change, sort of inherent to video generation in general. I think you don't have as much control, and curious if you're seeing that as a requirement and how you're thinking of approaching it.
Yeah, I think that's very important for post-training. That also depend on different use cases. Say you have, depending on your data, if your data have more different parameters you can use as conditioning, I think adding them into the training would definitely help. So like if you have additional like camera intrinsics, if you have additional cameras as condition, additional signals like audio, all of them can use as conditioning. The model is quite flexible for to add additional conditioning. For the diffusion model, we allow you to add it through cross attention and similar for autoregressive model.
Ethan, I have another question that's somewhat related. How much, I was a little confused about how much of the sort of the ability to generate realistic, sort of physics and physical model, like sort of world models, is due to training versus some like inductive bias in the model, and like what were the if the in as much as it was inductive bias, what were the key things there?
Mhm. So I think two key things are data and scale. So the model itself, as it grow larger and larger, a lot of the 3D capability, consistency, physics, intrinsics automatically appear when the model is bigger. And another thing is data. I think in the data, you need to have enough demonstration of different physical property for the model to learn. I'd say the model itself doesn't have a lot of inductive bias. It's just we're just using transformers. There's no like spatial attention, temporal attention, those kind of things.
Okay, got it. Thank you. It, if there aren't other questions, I actually have one more. So in the sort of in that the original diagram of the architecture, there's some things that I didn't understand about the positional embeddings. Like there's like two different positional embeddings or three different positional embeddings, I think. Yeah, so there's like this absolute positional embedding, and then actually there's another diagram that where there's another positional embedding that goes into the cross attention, I think. Yeah, this or well, it's I'm not sure what that is, that time step in this scale shift gate. So like I was kind of confused about what the purpose of all these are.
Yeah. So the timestamps is specific to the diffusion models. You know, the diffusion process, you're going through multiple steps to diffuse noise, and it becomes a clear and crisp video, right?
Mhm.
So during training, the process is like you randomly apply some noise to the tokens, and you also need to indicate the model like how much noise is added. If there are more noise, the time steps, it's a earlier step. The less noise, the time step is close to the end of the generation. So during inference, the model can gradually remove the noise and the condition on the which timestamp it is on. For the absolute positional embedding and 3D rope, those tell the model for this token which position it is in the video.
Sure. No, I guess I was just confused about what is the need for both the rotary positional embedding and also the absolute positional embedding? Like, why are both of those needed?
So not necessarily, but this can improve the model. In fact,
I see.
if you just use absolute position embedding, it can also work.
Okay, I see. Okay, got it, got it. Thank you.
Yeah, Ethan,
Hey,
can I ask a question?
yeah.
Yeah, so there was a comment in the chat about the use of vector quantization.
Yeah.
Now, how is that used actually? I don't think that it's used for selecting patches, but it could be used for the discrete latent space.
It's a training technique. Because basically for the autoregressive for the model, you need
Yes.
to have fixed set of vocabulary, and the input are basically indices, like this word is number one, number two, etc. So when you're training the tokenizer, you need to quantize them into the code book. When it's choosing for each patch, it basically look for the closest vector in the code book and pick it out.
Yeah.
Thanks, Ethan. I had a question about the size of the models that were posted to Hugging Face. How did you guys select those sizes? Did you experiment with larger sizes? Yeah, those are my questions.
So yeah, this is a first release of Cosmos 1.0. There might be bigger models in the future, and because when doing research, we want to go from small to big. We're not doing it one shot. And I think we're still in the infancy of word foundation models. And it's kind of like GPT-1 or GPT-2 stage of word foundation model. Bigger models will definitely come in the future.
Got it. Thanks. Was there any thinking in terms of like, well, this is good enough for most of the applications we see from, I don't know, customers or partners?
It's not good enough yet. It can be better and better. The model now has some emerging like physics property in the generative video. I would think it can get better.
Thanks.
Guys, so it looks like Swix passed the baton to me. He had to drop off a call or for an in real life meeting, and so I want to. If there are any other questions, encourage you to ask. Otherwise, I think we can take a little bit of time to discuss the next paper. And I actually have a hard stop in 3 minutes, so I need to drop off at that time. So first of all, Ethan, this is fantastic. I hope you keep coming back to these
Yeah.
these paper club meetings and like for even if you want to present someone else's paper rather than your own. Certainly, anytime you publish a paper, we definitely want to see you here. But if others publish paper and you think it's exciting and you want to share it, that we definitely would love to have you as well.
Thank you.
Yeah.
Thank you for hosting.
Yeah. I mean, Swix, but I'm happy to facilitate where I can. Are there other questions for Ethan before I'm not sure how much time we have really to discuss the next paper, but okay, does anyone want to volunteer? I think that I saw some chat, and I'm not sure about this, but I saw some noise on the Discord about people just picking things from the list of papers that are in our backlog, and then just giving brief, like sort of very fast discussions of those. Maybe I think that in the past we've taken 10 or 15 minutes to just go over, summarize the paper for everyone. Probably people won't probably pre-read, but it'll just be a good sort of way to understand in some detail what are the key points from the paper. So maybe I can post that. I think it's already in Discord, but I can post that in Discord. If there are people who are not on Discord, maybe I can suggest Swix also post that in Twitter or whatever. Is there, unless of course someone wants to volunteer to present a paper next week? Okay, somebody asked that for the Discord channel, if no one can dig that up, I suggest, I think it's on the latent space, on it, you can dig through the latent space Substack, or like maybe I think there's a website too, and you can find it there. Otherwise, you can hit me on X and I'll find it for you, or LinkedIn as well. I'm on both of them. My user handle is Haneke, or you can obviously also Swix, or anyone else here. Oh, there it goes. Okay, great. Okay, guys, so grab that if you need it. I'm gonna end the meeting, and yeah, I gotta go. So I'm gonna stop recording. Actually, I probably was supposed to stop recording. I guess we'll have to edit or whatever. And thank you very much. We'll see you next week.